welcome to the Birch Aquarium at Scripps and the Jeffrey B. Graham Perspectives on Ocean Science lecture series. My name is Cheryl Peach and I'm a program scientist here at the Birch Aquarium. It's my great pleasure tonight to welcome Dr. Andrew Dickson. He's a professor in residence here at Scripps Institution of Oceanography, and he's a specialist in carbon dioxide in seawater. And so a lot of us have heard about the effects of carbon dioxide in the atmosphere, and we've had a number of lectures here that have addressed that subject, but we've spoken less here about the effects of CO2 on seawater and what the implications are for ocean life and ocean chemistry in general. Andrew actually comes here from the University of Liverpool, where he received his Bachelor of Science and his PhD degree. And he's specialized here in doing very, very precise measurements of CO2 and ascertaining the quality of CO2 measurements in the oceans. And so it's a great pleasure to have Andrew here to talk to us about ocean acidification. What is it? Why should we care? Andrew, thank you very much.
Thank you. Good evening. Thank you very much for the opportunity to tell you about this. Ocean acidification is a phrase that is gradually growing in interest. If you were to look at the measure now of how interesting things are, Google, and were to look at ocean acidification, you would find coming up for 200,000 possible pages you could go to on this. This is, of course, a pittance compared to anything that people really consider interesting. Even global warming runs a few million, but it's getting there. So today we're going to talk about ocean acidification, as it's often referred to, the other CO2 problem. The principal CO2 problem, there's a substantial exhibit here talking about, which are the effects on the potential effects for the radiative balance of the Earth. But this, we're asking what happens when the CO2 goes into seawater. And it's becoming more and more discussed. This is a sort of bunch of different headlines I did a collage with, varying from German reports, the San Diego Union Tribune, Washington Post, Der Spiegel, Science Magazine, the Sunday Times in the UK, the LA Times. A variety of papers have all had articles about this. Most weeks there's one or two articles somewhere in a major newspaper about this. More recently, a variety of other articles here getting a little wider field. One talking about ocean acidification in the Great Barrier Reef, changes in sound traveling through the oceans, problems with squid as a result of increased carbon dioxide in the ocean, and possibly a potentially worrying one, the sea urchin fertility that was there. The Economist most recently had a special section about the ocean and its problems, and one of those articles entitled "The Curse of Carbon," a meltdown tinged with acid. The meltdown, of course, discussing the implications of temperature rising for glaciers and for the ice sheets. The tinged with acid referring to the oceans. So it's a subject that people are talking more and more about, and here I'd like to give you some idea as to what it is, and, as the title implied, why it should matter to you. My story starts talking about the work of Charles David Keeling, a professor here at Scripps who died in 2005. Now, Dave Keeling, through one of his major projects, was the very careful work required to give this detailed time series of carbon dioxide concentrations in the atmosphere. This started in 1957 at this little shed up on the top of Mauna Loa, basically a shed belonging to the National Weather Service, who were starting an observing system there. And over the years, these show monthly averages. As you go from year to year, as plants grow, the CO2 drops down. As the plants in the Northern Hemisphere drop their leaves and this decomposes partly, it goes back up again. But the most striking piece about this is this seemingly inexorable rise with time. And if we look at data from ice cores, we can see by collecting the CO2 trapped in the ice that for many years over the past 1,000, it was approximately constant. And it's only really at the start of the Industrial Revolution, 1750, 1760, that it starts to go up and up and up. We're now at about 386. This is an older picture. If you go into our display next door, it says, today's CO2. I'm afraid not. That was a year or so ago's CO2 level. It's meaningfully higher. The bar would be longer. Let's imagine looking back over time with these ice cores, because that's one of the things you can do. Here is looking back over 800,000 years. And CO2 levels went up and down basically between Ice Age and interglacial, right up to the start of that picture I showed you before, at around 280 parts per million. Then, there's almost this large finger sticking up at the end. The additional CO2 from the industrial use of carbon as a fuel source. Let's talk a little bit about quite how much carbon we're talking about here. This is a cumulative plot, so that we've added together all the things. Here, in about 2003, we're at about 1,100 billion tons of CO2. Now, we've got more used to talking about billions in the last few months. 700 billion for a bank here or there, 700 billion for some other problem. But a billion's a biggish number. So let's think a little bit about what 1 ton of CO2 might look like. If you were to freeze the CO2 into solid CO2, it's got about the density of water. So 1 ton of solid CO2 is about 1 cubic meter. 1 cubic meter is about the size under a good-sized office desk. 1 billion tons, 1,000 times 1,000 times 1,000 would be a cubic kilometer. 1,000 cubic kilometers of CO2, and pretty good, we're talking about a large amount. You think of Mount Soledad, it's a good deal less than 1 cubic kilometer, really. It's a big pile, and that's if you froze it out. Of course, in the atmosphere, it's present as gas. If you take that work of Dave Keeling and you ask, okay, how much extra CO2 is really in the atmosphere? You could say it's the difference between 280 and the number here in 1994, which was in the mid-360s, and you multiply that enough difference by the volume of the atmosphere, and you can say, okay, there's about this much is still in the atmosphere out of that total. Essentially, it goes in one of two places, into the ocean or into the plants on land. Now, that choice of 1994 as a time point on my previous picture was because there was a large survey of CO2 in the oceans in the 1990s, which showed quite clearly that there was extra CO2 that had come into the oceans. And this is a distribution around the oceans. If you imagine a line in the Indian Ocean coming up here into the Bay of Bengal, then this is the distribution in that ocean. The Atlantic, a line going up like that. The Pacific, a line up the center. The feature you see most obviously is that the oceans are being contaminated with CO2 from the top. The highest concentrations are right up at the surface, getting less and less as you go deeper. The Atlantic is a little bit different because in the North Atlantic you get cooling, salty water that gets sufficiently dense to sink down to the bottom of the ocean, bringing the CO2 with it. Because we did this survey all over the oceans of the world, and it was about 17,000 separate places and about 36 depths at each of those places, it was possible to estimate the amount of CO2 extra in the oceans that had come from the atmosphere. So if we go back to that picture and then add in the amount that was found in the ocean from that 1990s survey, it's like this. If you look carefully, you'll actually see it went a little far. And there was some extra CO2 basically involved in land plants. So the CO2 that we've produced by burning fossil fuels, by burning oil, coal, gas, ends up mostly in the atmosphere, the CO2 problem, but a meaningful part in the ocean, the other CO2 problem. So let's talk a little bit about what this does to the composition of seawater, because it's a little easier to follow some of the scientific discussion if we do this. And I apologize because this is more like chemistry than anything else in the talk, but I'm trying to make it straightforward, and if I fail, doubtless there will be questions, or somebody will tell me privately at the end. Let's imagine what's really in seawater. And let's imagine it's pre-industrial ocean surface water, an average typical ocean surface water in about 1750. Well, there's three components in seawater. There's dissolved CO2 by itself. There's bicarbonate ion, and there's carbonate ion. There's an axis break on this picture. I do that because I want to draw bicarbonate at about 1650 at the same time as I draw CO2 at a much, much smaller number of about 20, and I have to do that. This final piece is the total dissolved. That's this plus this plus this. And there's a pH associated with that, about 8.16. So the question then is, what happens when you add CO2 to this? Well, adding CO2 to seawater, it reacts with any carbonate ion in seawater to form bicarbonate ion. So when you dissolve more CO2, you essentially increase the concentration of this species. Some reaction goes and you get bicarbonate. So an increase in that species, because it reacts with the carbonate, decreases the carbonate, but the reaction goes across, it's increasing the bicarbonate. There are other relationships, for instance this one, which is between bicarbonate and carbonate, which essentially says that the product of concentrations is constant. We could rearrange that, and it says that the hydrogen ion concentration is dependent on the ratio bicarbonate to carbonate. So if we increase the top piece and we decrease the carbonate, the hydrogen ion concentration increases. Now, people don't usually talk about hydrogen ion concentration. This is one of the potentially confusing things about discussing acid-base processes. Often you see it referred to as a pH. pH is minus the logarithm of the hydrogen ion concentration. It's very convenient to do it that way because it allows you to cover a very large range of values with numbers that are manageable, but it's potentially confusing. But there are a lot of other logarithmic scales you hear about. You have the Richter scale for earthquakes. You have decibels for talking about sound intensity. These are logarithmic scales, and it's no different to that, and I'll point out both ideas as I go along. So let's go back to part one. We're going to add CO2 to seawater. Let's imagine we doubled or tripled the atmospheric concentration. So when the atmospheric CO2 increases, first, the total dissolved carbon increases. Some of it's dissolving into the oceans. It's changing the total. But in more detail, CO2 is getting bigger and the bicarbonate is getting larger. The carbonate, remember I said it was reacting with carbonate, the carbonate was getting less. So we get the carbonate going down and the pH goes down. Now, this helps you give some scale as to the figures. The pH going from 8.16 to 7.92 is 0.24 of a pH unit. 0.24 of a pH unit, really wouldn't worry you if this was the change in the pH of your pH-balanced shampoo. It's probably not a big deal. Similarly, it's not a big deal if this is the change in the liquid that your peas are canned in. These are all kinds of things that people are measuring pH on. But it's a meaningful change for the oceans. It's actually about 70% change in the hydrogen ion concentration. So a small change in pH is actually a significant change in hydrogen ion concentration. And you'll see the effects of that as I go on with this discussion. Well, we know what the CO2 has looked like from then, 800,000 years ago, till now. What happens as we go into the future? Well, of course, prediction is very difficult, especially if it's about the future. A reputable source. One way of thinking about this is to look and imagine what the CO2 concentration in the atmosphere might be. Here's one example of such a scenario. The measured is that blue line, increasing from about 1765 up to, in this case, about 1990. The red is a model, a scenario of the Intergovernmental Panel on Climate Change. When you put a scenario together, the question is not, what's the CO2 going to do in the atmosphere? That would be too simple. What you actually would say is, let's imagine what the world might be like, how many people there would be, what their economic situation would be, how much energy they would use, how much of that energy would come from fossil fuels, from coal and oil and gas. Having done that, you say, okay, let's imagine burning that. Some of it's going to stay in the atmosphere, some of it's going to go in the oceans, some of it's going to go into plants. We need a model that apportions that. From that, we get this picture of how much stays in the atmosphere. This particular scenario looks rather boring as IS-92A. It's got a more interesting title. People often refer to it as the business as usual scenario. And in a few moments, you'll see why that's perhaps an appropriate pseudonym. More recently, the most recent IPCC took much more detail on possible scenarios, and there's a range of, if you have a particular way of organizing the economy and it's fossil fuel intensive, whoa, heads off. On the other hand, if the world is organized somewhat differently and you're taking care to switch to different energy sources, levels off. Who knows what will happen? Prediction is difficult, especially. The black line here is that IS-92A. It sits sensibly in the middle. So it's a plausible thing for me to talk about as a what-if scenario. We go back now to those CO2 emissions, and instead of giving you the total, I'm telling you how much per year. 25 here, just about 2002. Now it's up here. In case you've been in the climate exhibit, I should just point out that there's two different accounting schemes that are used for this. I've got this in tons of CO2. Very often, and I think in this exhibit you will see it in tons of carbon. So I think it mentions 7 tons of carbon, probably nearer 8, sorry, not tons, billion tons of carbon, gigatons per year. So the story so far, if we add in that IS-92A scenario, that's the scenario's addition of carbon, increasing every year, the same way pretty well as it has done since 1950. Business as usual. You can imagine having a model that carried this even further into the future. The one that Caldera and Wickett used here was essentially say, we're going to run out of coal. And so this line has to turn over and come back down again. Now, this is the use of fossil fuel. What does that do for the CO2 in the atmosphere? The story so far, this pitiful little blue piece. The red, if you continue on that trajectory, we get to, this suggests going to very high atmospheric levels relative to today. Today's about 386. There's two things to point out about this plot, which are very important in any of these discussions. Number one is at this point here, you started cutting back on the amount that was being burned. But the level in the atmosphere had gotten nowhere near its maximum. Just because you start cutting back, there's not this instantaneous response. It keeps increasing in the atmosphere. The other piece of bad news is look at this line here. When does this line get back down about the level of the blue? Whoa, somewhere out on the balcony. This was 3,000 in the year of our Lord 3000. You know, those of you that worry about your grandchildren and great-grandchildren, that's still a little further on. So the next striking thing is once you put the CO2 in the atmosphere, it takes a very long time to get it back out by natural processes. The natural process dominating the speed at which that is coming out is it's dissolving into the oceans. And to get it into the oceans, remember I showed you the picture, it was just at the surface of the oceans. That is because the oceans are only mixed slowly. You put the sugar in your coffee and you stir it once every 1,000 years. That's about an ocean stirring. As a result, this comes down with that time scale. But putting that CO2 into the ocean also changes the pH in the ocean. It changes it here a little bit more, about 0.1 of a pH unit at about current day. It's actually about 0.12 now. Quite a small change, 30% in hydrogen ion concentration. As it goes up, the surface pH goes up and up. As it comes down, gradually the surface pH starts to come down again. But as it mixes deeper, the effect, which was pretty well nothing in the deep ocean early on, gradually goes down into the deep ocean. So, a model. What could happen? On the small time scale we've been measuring it, this is what is happening. Here are pictures from the Hawaii Ocean Time Series, HOT, and the Bermuda Atlantic Time Series, BATS. The acronyms are chosen by the people who give them, so there's no foolish consistency. The change in pH, you can see here most clearly at Hawaii, the pH going down over this quite limited time period, about 10 years. Going down measurably. The implication of that and other CO2 measurements done at that location are that the carbonate ion concentration is going down. And then parallel with that, this thing that's referred to as omega arag. This is the saturation state of aragonite. Aragonite and calcite are different crystalline forms of calcium carbonate. You essentially have a reaction between the solid and the ions in solution, an equilibrium constant defining its solubility. Aragonite is more soluble than calcite. And you'll often, as I said, see reference to the saturation state. And the saturation state is essentially the ratio between what you actually found in the seawater and what it would be if it were at equilibrium. And what does that mean? Well, if that number was less than 1, you'd expect the mineral calcium carbonate to dissolve. If it was equal to 1, it would tell you that it was at equilibrium. If it's greater than 1, then supersaturated calcium carbonate can form. Here's a map of the oceans showing the aragonite saturation state. Estimated, this, as we start, is the good old days, 1765, 11 years before the US forms. And we see that most of the oceans are actually quite highly saturated, saturation states well above 4. The high latitude oceans, they're significantly lower, 2, 2.5. As we go along with time, and we keep adding CO2 to the atmosphere, some's coming into the ocean, you see this change in the distribution as CO2 goes in. Year 2000, we're there today. Moving on, following that atmospheric trajectory I showed you before, till we get to 2100. It's more obvious now that the picture has measles. These little black are current day locations of coral reefs. The maroon ones are cold water, locations of cold water corals. We'll come back to talking about what this means for corals in a few minutes. But clearly, changes in this saturation state. Now, there's a lot of organisms that have calcium carbonate. They're the very pretty ones from these Emilianae Huxley coccolithophores. Ones like that substantially make up, say, the famous white cliffs of Dover, them and related species. Pteropods, these are essentially planktonic snails. Here, this one, Clobbridge seculifer. Essentially, this small piece here is calcium carbonate in it. Whole variety of bottom-dwelling organisms, benthic ones, from coralline algae, benthic foraminifera, corals, mollusks, things like these echinoderms, the brittle star, crustacea. Well, let's look at a worst case. One of the species that's often been thought of as a poster child for ocean acidification is this pteropod, or pteropods like this. What we're seeing here, the pteropod, or a pteropod like this, was exposed to seawater at a CO2 level equivalent to that predicted for 2100 in the region where it lives, which are the high latitudes. In that case, it was actually somewhat undersaturated. And we're looking at the shell of the pteropod under a scanning electron microscope to give you a picture of it. Now, if it had not been exposed, it would be a very smooth edge. But what you see are these little sites referring to different places on this one shell. It's clearly corroded relative to a pristine shell. It's starting to dissolve. This was happening in a couple of days at this concentration. Now, pteropods are widely distributed, particularly in the high latitudes. They are a significant part in the North Pacific of the diet of pink salmon. So, if the acidification of the oceans were to make it untenable for pteropods to live there, what would this mean for pink salmon? I'm not somebody who can tell you, and I've not spoken to anybody who really thinks convincingly they can tell you. You know, you have two possibilities as I see it. One is the pink salmon act like my daughter and say, if it's not a pteropod, I'm not going to eat it. This would be problematic. On the other hand, they may be more like me and say, okay, what else is there to eat? And there would be other things that came or were appropriate for salmon to eat. One of the difficulties is that these knock-on effects we don't really understand. We know that adding CO2 to seawater changes the saturation state, that will be problematic for pteropods. But what that means for the larger ecology, no matter how beautiful this is, it's really the larger effects that are probably going to have the most influence on our lives. We're really not sure. Let's go on to talk about corals. Here's an interesting experiment that was done in Biosphere 2. I don't know if you've heard about Biosphere, but essentially it was a totally enclosed resort, perhaps not resort, but the idea was that you had a totally enclosed environment where there was vegetation growing, where people could grow their food, could live there. The photosynthesis would create enough oxygen. The decomposition would replace things back, and it would be a small, self-contained world. It didn't work so well. They staggered out after a number of months, feeling a little unhappy. But it was later leased to Columbia University, who used it as an experimental facility. And one of the pieces of this was a large tank swimming pool for growing corals. Basically, they could have a coral reef, many different types of corals, a mixture of corals, coralline algae. And the people doing this study changed the composition of the water. This was sort of definitely what one would refer to as bucket chemistry. You take a bucket of acid and tip it in, stir it round. I mean, as I said, it's a swimming pool. You need a big mixer to stir it round. And you change the composition. What they found when they measured the rate of coral growth, the skeleton, is that as you lowered the carbonate ion concentration, that is, you lowered the saturation state, they grew less well until finally they started to dissolve. Let's put a little bit of context on there. On this picture, that's about pre-industrial. The scatter around is partially probably due to lousy measurements, but probably also due to the fact you've got a mixture of corals and things. They don't all behave the same way at the same time. There's a lot of experiments on this. It's not just one experiment done. It's a whole series of experiments over a number of years put together on one picture. So that we're clearly creeping down this line. And this is a problem if you're a coral, because one of the key features for a coral is it lives in an area where there's substantial mechanical damage near the surface of the ocean with the waves. And so if they're not continually calcifying, they eventually end up where they're not in the ideal place to live anymore. They have to calcify at a sensible rate to do well. So let's go back to that picture I showed you and just give you some examples. Now I've classified this aragonite saturation state from the coral's point of view. Optimal, these dark blues. Extremely low, coming down from 3 and below. And, you know, okay, in between. Well, moving from good, fine to not fine, so pretty good, not so good, in between. As you add the CO2 to where we are today, you see that we shrank in these dark blue areas, but that most of the corals are still in those kinds of reefs. This really shows that coral reefs have been forming where these numbers were really quite high, that today's coral reefs, which started, many of them, hundreds of years ago, have built up like this. As you go through to mid-century, yeah, it's mostly in the middle kind of ground, and by the time you follow that picture out to the end of the century, corals are mostly in less desirable conditions from the point of view of a coral. Whether this is the major problem for corals is still to be debated, of course, because you could hear any number of talks about the problems that corals face, from bleaching, from temperature going up, to viral attacks, to things like the crown of thorns, man's effect either just polluting the area where the corals are growing, or worse yet, dynamiting them to take the calcium carbonate away to make cement. Corals have got a lot of problems, and ocean acidification is but one of them. Other species. Here's some work that was done on shellfish, on mussels, and on the California oyster. These are at significantly higher CO2s than would be found by 2100, these experiments, but again they show the same basic idea. The calcification rate is going down the higher the CO2 level. There's a relationship between calcification shape and CO2 level that suggests that more CO2, less calcification. We can look at phytoplankton. Here, we can look at these coccolithophores, and they're really very attractive, tiny creatures. You need a scanning electron microscope, but then there's a huge amount of detail in these liths. But if we grow them at higher CO2, they don't look quite as elegant. I'm not a physiologist, and I'm not an algal physiologist. I don't really understand what this means for the energy involved for these organisms to grow these liths. They're still supersaturated, they can still grow them, but they're obviously putting more effort into it, it seems, one way of looking at it. And you can see that again, that the calcification rates go down as you increase the CO2 or decrease the carbonate ion concentration. So bringing all the data that people have done over the years together, what you start to see is, here's one. If the PCO2 was 560, that's double pre-industrial. On that business as usual, it's where it would be in 2050. If I were to start eating right and exercising, I might just make it to 2050. You never know your luck. My parents wouldn't have, but I might. They're all showing a reduction in calcification. These ones, quite big reductions. These ones, quite small reductions. But all these species are doing that. These four at the end are actually looking at coral reef environments that have been studied where you've got a whole different group of corals, just not just a few organisms in a fish tank. A recent paper from the beginning of this year looked at number of species studied from different groups. And the idea here is if CO2 goes up, does the physiological response go down, go up, stay about the same, or have some kind of optimum? Most of them went down. Not every one. Some improved. Higher CO2 was good for those species, perhaps. So it's not a certain thing, but the worrying factor is that many of them go down. Let's go back to those headlines I pointed, because I've been talking mostly about calcification, but I just wanted to remind you that that wasn't the whole story. It's part of a story: ocean acidification, global warming, and the Great Barrier Reef. This was a scientific paper in Science that came out in December last year, and they showed that the calcification rates on the Great Barrier Reef had decreased by about 15% since about 1950. And they were looking at corals that had been growing for a few hundred years, so it was a quite obvious change. Why? They don't really know. But ocean acidification is certainly something where small lab studies have shown that you would expect this, and here they were finding it looking at the barrier reef. This work, sound travels further underwater as world's oceans become more acidic. You're changing the composition of the seawater. You're reducing the carbonate ion concentration. That and its interactions with other ions in seawater changes the sound absorption, so sound can travel further in the oceans. Is that good? Can the whale go to their buddy, hi, over a few more 100 kilometers? Or is it going to end up like a loud party room? You can't say, but you know, that also is hidden because we have huge amounts of ship transport in the oceans that have made it so much louder anyway that this may yet be a small effect. But it's clearly one that does occur when you change the composition. Looking here at jumbo squid, they basically asked how much oxygen these squid used as they lived. And as you change the CO2 content over the range going up to what you would expect in 2100, the squid needed more oxygen to do the same things. So they were using more effort, more energy to achieve the same thing at higher CO2. Thus, presumably, they would need to get that more energy from somewhere, and this could be a problem. This last one was looking at the motility of sea urchin sperm, and it slowed down. It was obviously less effective sperm in the higher CO2 waters. Very simple lab experiment. But lab experiments, you know, we need to know a lot more. For one thing, we really need to go beyond these simple culture studies. We ask ourselves, what are these effects on ecosystems? How can you think about the consequences of this for ecosystems? Why? Well, you'd like to say, well, this is where you would expect a problem. Is this a big enough problem to make you change your ways? That's perhaps one way of looking at it. We need to ask, can organisms adapt to these changes? Because a typical experiment is you have the organisms and you put them in a changed condition, or you move them to that changed condition quite quickly. You want the results. You've only got the graduate student, and he's only going to be there for a few years. You'd like to get the results done in a finite amount of time. Well, that's not what's happening. The oceans are going up steadily over tens of years. This is not how you're doing the experiments. Maybe some organisms have a capacity for being comfortable in these higher CO2 environments, that they can sort of switch on the way that their genomics work to deal with that. We don't really know. We're just starting to investigate genomic studies on organisms to see the stresses from ocean acidification as a result. We'd like to know what the whole ecosystem. I gave that simplistic view of salmon and their food because that's a very simple ecosystem. Carbonate species, I eat you, you wanted to eat the salmon. But of course many ecosystems have many, many more interactions. And what would be the effect of one or two species in this ecosystem having problems? I think it's fair to say we don't know. The ocean carbon cycle. Are phytoplankton going to grow more? Some of those ones that improved, basically where there was more CO2, they photosynthesized better. But if that happens, what does it change about the carbon cycle in the ocean? Is that a good or a bad thing? We don't know. Unfortunately, that's, I guess, the refrain for much of ocean acidification. We just don't yet know. I hope the word yet is appropriate. Mitigation strategies. What can you do about this? Well, it's in that context I gave you this image of 1,000 billion tons of carbon dioxide. It's not so easy to say, well, I'll just put it away again. We're talking large amounts. And it may be that there are ways we can think about this that make a difference, but it's not yet clear they're ones that work well. Who knows? Maybe that list should be 4 times as long. There are other things that I'm sure we need to understand better. So, to summarize about the changes, here's a picture. The pH of the glacial times, the bottom of that up and down curve of CO2 for 800,000 years, was in that region. It's a little dot because we've only got a few ice cores. They're all about the same. It don't talk about there being a whole ocean there. It's a simple picture. At the glacial part, pre-industrial, be around here. So we were going back and forward between these pHs. Since then, the pH has dropped down. And if we look around the oceans, there's a whole range of pHs. The main center is there, but it's a wide range. This particular report to the German government drew a guardrail. Here is where you would be towards the end of the century. The idea of this guardrail, and they used it a number of times in the report, was we really shouldn't go beyond this point. I tried to ask myself why they drew the line there, and I couldn't see anything more in my reading of the report than back here in pre-industrial days, we assume it was okay, and this is only 0.2, so maybe 0.2 isn't too big a problem. That's not a very scientifically based judgment. The 0.2 is echoed in EPA documents about desirable pH changes in power station cooling water if you take seawater in and put it out and things like that. But it's just a number somebody made up that they felt comfortable with. Really why it's that number, because this starts to matter. If you're saying we can't take the CO2 above a certain level, and that level's quite low, it's a lot of effort not to take the CO2 above that level in the atmosphere. Especially, remember that I showed you, I said, the moment, even if you start cutting back on your use of CO2, the atmospheric level keeps going up for a while. And once it's up there, it only comes down very slowly. So, is that a good God? I don't really know. And then, just to sort of round off, there was a big meeting, the Ocean in a High CO2 World in Monaco, and the scientists put together what they're referring to as a Monaco Declaration. It's a feeling that this would get better publicity in press. The Monaco Declaration, if it does get adequate publicity, you should hear of it in about 8 days' time. It will be put out with the Prince of Monaco as a strong sponsor, saying that this is important. What does it say? Well, that's what I've been telling you, right? That too. That curve was going up. It's accelerating. Severe damages are imminent. In cultures, that's certainly the impression you get. Why would you believe that wasn't true for the natural environment? Undue optimism would probably be your only excuse. Ocean acidification will have socio-economic impacts. It's clearly going to change fisheries. It clearly could change coral reefs and their effect for a tourist industry. Are these big numbers? Well, as I said, 3 months ago they would have seemed like big numbers. Now that people are talking about packages to improve the economy, perhaps they're not. But it's problematic if you imagine that shellfish or fishing are having problems. The recovery is both the CO2 going down, which I've told you about, but of course, if you want organisms to come back to how they were before or some better thing, it's going to be slow. And here, really the kicker. There's been discussions. There was an article in a UK newspaper some while ago saying, scientists say it's time for Plan B. Plan B was saying if increasing global temperatures are a problem, maybe we could do this by changing the radiation balance, putting particles in the upper atmosphere to reflect it, setting out, little sunshades above the Earth. Elaborate, lots of fun to think about, but does nothing about the CO2 levels. Does nothing about the CO2 levels. CO2 levels are related essentially to how much CO2 you produce by burning fossil fuels and how much of that is put out into the atmosphere as its exhaust. If you catch it all and can hide it underground, and there are efforts afoot to try doing that, then you're not really adding to the problem, but you're creating other problems. There was more to it. I don't know how well you can read these, but basically one says, spend more on scientists, improve understanding of impacts of ocean acidification. Try to understand how important this really is. The links between economists and scientists. Try and understand if this were to happen, how big a problem would it be? Scientists always believe that if they could only explain it properly to policymakers, everything would be wonderful. And so that line is here too. And it may be partly so. But as I'm sure you know, policymakers have many things that they're trying to balance, and the science alone is not always the same story. But the belief is that if there were policy-relevant questions that needed science, it might be good to encourage that. And then this last, to prevent severe damages, imagine you can have ambitious plans to cut emissions. Now, if you're interested in more or a different way of doing this, there's actually a movie. This movie is essentially the picture is a Norwegian fisherman imagining what he would be leaving to his grandson in the oceans because of the problems of ocean acidification. And he talks to a number of scientists, but it's somewhat of the up-close and personal discussion as well. The world premiere is planned for March 14th at the DC Environmental Film Festival, the Natural History Museum. So a different point of view, and it might be something that you would enjoy looking at. Now, I opened this by showing a lot of press cuttings, and one I said, the Los Angeles Times. The Los Angeles Times had this great photograph. This is Ken Caldera, the person that put that simple model together showing if CO2 goes into, if you burn fossil fuels, you get CO2, you get pH changes in the ocean that I showed. Here he is with the Moss Landing power station, staring thoughtfully into the distance, holding this bottle of seawater? Who knows? Sewage? I'm not certain. But it's a very posed picture. And I saw that, and immediately it reminded me, the Los Angeles Times kind of likes these pictures. One I remembered was this one. This was a graduate student of Dave Keeling looking at a flask such as the ones they collect CO2 in at the South Pole. It's not really one of those flasks, because those flasks are covered with medical tape so that if you drop them or the glass breaks, it doesn't spray everywhere. This is one designed for a photograph without the tape on. Standing on the old Scripps pier, posing. And I thought, you know, I've seen that picture before too. Hamlet reflecting on the inevitability of mortality. Alas, poor Yorick, I knew him, Horatio. I'm wondering quite what the LA Times is implying by those pictures. I hope not that a problem is inevitable for us. Thank you. You're right. The question was pointing out that although I'd spoken about CO2 concentrations, of course, the first CO2 problem, the temperature effects, are also there. And clearly, in an oceanic setting, both these things will be going together. The only system for which that has even really been looked at adequately at the moment is looking at coral calcification. And the bad news is increasing the temperature makes it worse. It's something that scientists need to study more and understand not only those relationships, but the consequent relationships of changes in mixing in the ocean, because the temperature effects affect the stability and the winds, and what that will mean as well when we are adding CO2 too. So it gets, sadly, the first wish of the Monaco Declaration, that you spend more on the science. There will be places for the money to go. They're starting to. The question is basically asking that when you're modeling this and worrying about it from the other side, how much CO2 is remaining in the atmosphere, do current models take into account the changes in the ocean that are the result of adding more and more CO2 and therefore changing its ability to take up CO2? The earliest models didn't. They had a standard fraction that was used. Modern models do take that up and take that into account. And that's, of course, an important piece, because one of the concerns is how much CO2 is going to stay in the atmosphere, because that still is, especially on Google, the primary problem, the global warming. And it's a real concern. And modern ones, as you change the ocean mixing, it changes how much CO2 is taken up by the oceans. There's a hint today that it's getting less and less, but it's still only a small amount less. The question here is really asking, are there examples in the past, and he's referring to a NOVA program that referred to one that would be similar. The one that's perhaps best talked about is, I think, the Paleocene-Eocene thermal maximum. It's not hydrogen sulfide. The idea that people think here is that a large amount of methane was released, and this changed the CO2. It changed the temperature suddenly on the planet, suddenly over many thousands of years, maybe it looks like. Quite quickly, though, for geological changes that can be seen, this is a number, I think I'm not an expert in this, but in the 20, 30 million years ago, maybe a little bit even older than that, what happened then was that many of the organisms that were leaving carbonate at the bottom of the oceans completely disappeared, and there was no carbonate sediment forming at the bottom of the oceans. And then gradually, carbonate shells started appearing in the sediments again, and it all came back. But the size of that dip was 1,000,000 years. Not, this economic downturn is 2 years maybe, 1,000,000 years. So the older ones suggest that when you get this far, yes, things do recover, but they recover slowly. And that was, again, I think one of the things referred to in that Monaco Declaration, was that there was this possibility of things recovering, but the biological response recovery that we can infer from geological studies is very slow.